Hello, my name is Brendan Quinn, and I'm the team lead of CUAir. I'm a senior at Cornell, and this is my 4th year on the team. My experience with unmanned air systems is with the implementation of autopilots and their peripheral systems. On the competition team and on Flightline, I'll serve as mission director, instructing the team when to complete tasks.
My name is Nikita Yermoshkin. I'm a junior and this is my 3rd year on CUAir. I am the team's electrical lead and will be the safety pilot on the Flightline.
Hi, I'm Troy Joseph and I'm a junior. This is my 3rd year working on the autopilot system for CUAir, and this year I am the sub-team lead of autopilot. On the Flightline, I will be operating the autopilot ground control system.
Hi, I'm Yasmin Mushtaq. I'm a junior. I've been on CUAir for 3 years. This year I've been in charge of mechanical components, including the electronics bay and payloads, and at competition I'm going to be the spotter and mechanical representative.
Hello everyone, I'm Rahul Madana Hale, and I'm a junior studying computer science. I've been on CUAir for 3 years now, and now I'm currently the distributed systems team lead, where we work on MDLC, which is the manual detection, localization, and classification. On the Flightline, during competition, I will be the distributed systems operator.
Hi, my name is Eric Dye. I'm currently a junior and this will be my 3rd year on CUAir. My UAS experience is primarily on the electrical and distributed systems subteams where I deal with hardware and software systems as well as integration. On the Flightline, I will be managing the antenna tracker and communication systems as well as MDLC.
Hi, my name is Ram Valenki and I'm a sophomore here. This is my 2nd year on CUAir and my experience with UAS technologies is limited to those 2 years, which included working on communications software and distributed systems development. So on the team, my role is as a distributed systems developer, which entails writing the software infrastructure from communicating to the ground to the plane and vice versa. On the Flightline, I'm responsible for the MDLC clients and also the imaging system.
My name is Jesse Lupica. I am a junior. I have been on CUAir for 2 years. My primary experience with UAS technologies has been with autopilot and ground station software. On CUAir, I work with autonomous obstacle avoidance systems. On the Flightline, I will be the sense, detect, and avoid operator.
Hi, my name is Grant Mullitz. I am a senior. I've been on the team for 3 years. My experience with UAS technologies focuses on computer vision techniques for detection and classification. My current role on the team is Vision Sub-Team Lead, and on the Flightline I will be managing the ADLC Automatic Detection, Location, and Classification System and participating in MDLC Manual Detection, Location, and Classification of Targets.
Hi. My name is Joshua Williams and I'm a junior with 3 years experience on the team. My experience is primarily with airframe design and I'm the airframe sub-team lead. I'm also going to be doing MDLC at competition. For the 2017 competition, we modified our past year's aircraft. We constructed another modular airframe with a composite material fuselage attached to a carbon fiber boom and polystyrene foam core wings and tail laid up in composite materials. However, this year we increased our wing size to increase efficiency and decrease airspeed. We tested our airframe in over a dozen test flights. The aircraft has a maximum speed of 20 meters per second and a cruise velocity of 14 meters per second.
The electrical system is similar to our previous year's hardware, featuring a 5.8 GHz Wi-Fi data link, 900 MHz telemetry link, and a 433 MHz frequency hopping RC backup link. We're using lithium polymer batteries to power payloads, propulsion, and autopilot systems. This year, we increased the modularity of designs to make replacing parts faster and simpler, as well as simplifying several flight-critical board designs to increase safety and reliability.
To succeed in the detection, localization, and classification task, and the airdrop task, we've implemented a distributed system that has servers on the ground and on the plane, and they communicate over HTTP. Our fault-tolerant systems are prepared for communication failures. We have a gimbal server on the plane that controls the orientation of the camera, a camera server that takes pictures, and an airdrop server that runs an algorithm to drop the water bottle onto a particular location. Data from these plane servers, as well as telemetry data, are sent to the MDLC ground server. The MDLC ground server is connected to multiple web application clients that allow users to tag targets, merge common targets, and manage settings and safety mechanisms on the plane. The MDLC ground server also runs a localization algorithm on the targets and then sends these targets to the competition interop server.
The CUAir team is confident in the ability of the THEA system to complete all competition tasks this year. The THEA system has been tested in over 20 test flights, testing various mission objectives. In full mission tests, the THEA system has reliably and accurately completed waypoint navigation, obstacle avoidance, air delivery, and object detection, localization, and classification tasks.
Software testing for all of our system includes not only unit testing to ensure code coverage with frameworks such as Mocha, JUnit, and PyUnit, but also continuous integration to make sure that any additional code to our codebase doesn't break any pre-existing software.
The THEA Autopilot firmware requires an involved tuning process to fly with optimal maneuverability and safety. To tune the autopilot, we first configured the PID stabilization algorithm using rapid in-flight movements. We next configured the longitudinal and latitudinal control algorithms with airspeed and throttle measurements. Finally, we configured autonomous catapult launch takeoff and autonomous belly landing. The entire tuning process took 200 minutes of flight time to complete, 60% of which was in manual or pilot-assisted modes. Once we completed the tuning process, we flew an additional 300 minutes of flight time, only 10% of which was in manual or pilot-assisted modes. The THEA system has flown 20 flights with waypoint navigation capabilities, attempting to fly over 400 waypoints. In all our testing, THEA has achieved an average miss rate of 25 feet, attempting to fly over 350 of the waypoints within the 100-foot threshold. This displays a strong improvement over our previous system, Theseus, which had an average miss rate of 80 feet.
THEA's autonomous obstacle avoidance system has been used on 11 different test flights and tested on 85 moving and stationary obstacles. In these flights, the obstacle avoidance system has conducted 94 autonomous flight path rerouting events. This has led to 57 successful collision avoidances throughout the testing process.
All images sampled by the Z camera have a 4K resolution and are sampled at a rate of 1 image per second so as to ensure full coverage of the field. Some techniques to improve the image quality are reducing shutter speed and increasing aperture to minimize the warping effects of the rolling shutter, and also increasing saturation and contrast to improve the distinction between colors to help our image detection and classification systems.
Images captured by the camera are passed to the Autonomous Detection, Localization, and Classification System. The system detects regions of interest in those images by the SURF detection algorithm. Those regions of interest are then segmented into alphanumeric and shape regions. The alphanumeric and shape regions are classified by proprietary and library classifiers. The color is then classified by a proprietary classifier for each of those targets. Throughout the detection and classification system, there are false positive checks to verify that the region of interest is in fact an alphanumeric target. The system was tested on real data taken from the current imaging system. There were approximately 2,000 images that the system was tested on. From those tests, we got accuracies of 60% for alphanumeric classification, 60% for shape classification, 70% for shape color classification, 30% for alphanumeric color classification, and 75% for overall precision for target detection.
We've run 20 test flights where we have tagged and ran the localization algorithm on a total of 120 targets. We even made sure to test the localization algorithm on a uniform distribution of target orientations. The latitude and longitude of the localization algorithm have a maximum bound error of 50 feet from the target's true location.
The airdrop system was tested at Cornell's drop tower 4 times and on the aircraft 15 times. The payload survived 100% of the time, both at the drop tower and from the aircraft. At the drop tower, the payload landed an average of 5 feet from the target spot, and from the aircraft, the payload landed consistently within 60 feet of the target spot.
In full mission tests, the CUAir team tested each system against how it was expected to perform. If any system did not meet standards, backup options were employed. As the team tested each system independently before integration, any systems that did not meet standards were able to be fixed before mission testing. The navigation system was tested throughout the year with mock payloads to ensure the aircraft was reliable and ready for mission testing well in advance. The object avoidance system was tested alongside waypoint navigation to ensure reliability and safety. To improve accuracy and consistency, the obstacle avoidance system is able to be manually assisted to provide safer and more optimal paths. This system is constrained to only allow paths safe for the plane to fly. In mission testing, the air delivery payload was found to drop reliably in repeated testing from the plane. As the payload remained intact in 100% of the drops, and landed safely within 60 feet of the target. The CUAir team is confident that they will be able to complete the air delivery task. Object detection, localization, and classification was performed in all of our mission tests. The system was altered to ensure that the camera settings would work in all possible lighting and weather conditions at competition. Additionally, the system is able to autonomously reconnect to the imaging network in case of temporary disconnection. If reconnection is not possible, the system will continue to take images and process them upon landing. With assistance from the autonomous ODLC system, images from a 20-minute flight are able to be processed in under 5 minutes. From repeated mission testing, these systems have been shown to work together reliably and consistently.
Over the course of the year, the team conducted several test flights in which they attempted mission tasks. Of these flight tests, the following are the scores from the full mission test that the team scored itself based on the rubric provided in the mission demonstration section. 86.1%, 82.3%, 78.8%, 83.0%, and 82.7%. For each section of the mission demonstration, our average and expected scores are as follows. For timeline, the team averaged and expects to score 60% with a setup time of 12 minutes, flight time of 24 minutes, post-processing time of 6.5 minutes, and no time taken. For autonomous flight, the average score was 66% with 95% of points in autonomous flight, full points in waypoint capture, 52% of points in waypoint accuracy, and less than 1 out of bounds per flight. The expected scores are 88% overall with full points on autonomous flight and waypoint capture, 75% of points in waypoint accuracy, and no boundary violations. For obstacle avoidance, the team averaged 58% with 85% of points in stationary object avoidance and 31% in moving object avoidance. The expected scores are 70% overall with 90% in stationary object avoidance and 50% in moving object avoidance. For object detection, localization, classification, the average score was 92% with an average of full points in characteristics, 86% in geolocation, 80% actionable, 75% autonomy, full points in interoperability, and no extra targets. The team expects the same scores for this section. For air delivery, the team averaged 71% with a bottle landing an average of 42 feet from the target and no damage. The team expects to score 73% of points with the bottle landing no more than 40 feet from the target and no damage penalty. For operational excellence, the team averaged and expects to earn full marks. The average score overall for these mission tests was 73% and the team expects to score 82% in the competition mission demonstration.